This facility is extremely rare in the sense that it produces high energy that bombard our electronic components in a simulated fashion that allows us to get them ready for space applications. When I say it's extremely rare, the energy levels at this location is super unique. There is a ton of safety precautions to ensure that we're protected from the radiation that is being exposed to a variety of different mediums. So many moving pieces that are going on here. This is exciting to see. So why don't we pop in and take a look at what makes NSRL NSRL. So we just arrived at the NASA Space Radiation Laboratory, also known as NSRL. This facility is extremely rare in the sense that the energy levels at this location is super unique. Now, this is where all of the testing occurs at the NSRL site. We're about to walk in to where they have covered a spectrum of different types of tests for not only NASA, but also for commercial and national security related space applications. So why don't we pop in and take a look at what makes NSRL NSRL. So we're here at NSRL, sitting down to discuss, some of the radiation testing that is ongoing at this facility. Now, there are active tests that happen here regularly. I mean, today is no different. And with that, so we're here now talking about some of the stuff that happens in this facility. So why don't you guys introduce yourselves, give a little background on what NSRL is and what you guys do here.
I'm Trevor Olsen. I've been working here for about 7.5 years now. My background is in nuclear engineering, nuclear physics.
My name is Don Hornback. I'm a National Security Program Director at Brookhaven. Been here for 3 years. Prior to that, I worked in government. So I've done program management and actually have a background in particle physics. So that's why I'm trying to meld national security and particle physics at Brookhaven.
Yeah. So this is the control room, and this is our main display, so to speak. Each of these squares over here is a magnet on our beamline. So these are all responsible for creating that shape. We've got series of dipoles, quadrupoles, and 2 octupoles. Those are the things that are making that square beam shape.
What is that? So the users, the listeners that are tuning in, what are all those different
So dipole, quadrupole, that's referring to a type of electromagnet and how many pole faces there are. So if you imagine a schematic where there's like a north and a south, it's basically each one of those is a pole. So we have magnets that have just a north and a south, so to speak. And then we have quadrupoles, which will have 2 souths and 2 norths. And so you're creating a shape of a magnetic field. And that's what's actually bending the beam into its particular shape.
So you're molding it into what you want.
Exactly.
Because it's going to be all chaotic when it's going in there. Correct?
Yeah, that's right. So it starts off as basically a small little circle, and Gaussian shape. That's what's produced in the synchrotron just naturally, and we extract that beam. And as soon as we do, we're starting to use the quadrupoles to widen and elongate these transverse sections. So at the end of the beam, it'll produce that square shape that we're going for. We have a number of plots up here. So this plot is showing all of the different things that are happening in the accelerator cycle. So you can see that this giant purple line is actually the main magnet of the synchrotron. So the beam is accelerating every time it goes around in a circle. And during that course, you have to increase your magnet strength to make sure that the beam stays confined in the synchrotron. So when we get up to the max energy here, we turn off the RF cavities. This little square here is what's actually driving the energy gain of the beam. And then we start extracting it during this window at this nominal energy, the intended energy that we want.
So this is the sweet spot.
Yeah, this is exactly where the beam comes out into the lab.
So the way that I'm thinking about this in my head is that you're flushing out all the stuff that you don't want, and you want the sweet spot of the beam.
Yeah, it's not ready to be at the energy that we are desired at until it's at this flat window, and then we turn on other magnets that begin to kick it out into our beamline.
So then you see this red portion right here. What is the significance of this? Because I see a lot of activity happening in this area.
Right. So right now the beam is so low intensity that you can't see the signal of the beam. We can show you what it would look like if there was high intensity of the beam, but the red line specifically is a manipulation on top of the purple line that is going to push the beam outwards to where we peel it off from the circle synchrotron.
Okay.
So that's what's allowing us to begin extraction, as we call it.
Okay. So all of this is happening in real time, right? These are active displays of what is happening in the back room that
Exactly.
we were just in.
Yeah.
And as a user that comes in here, each of these different pieces are being monitored in real time to ensure that the test is going according to the way that we drew it out before it came in, correct?
That's right. So the users will ask for a specific ion and energy of these ions, and then the controls are designed in such a way that we get exactly that in the target room. So it's actually thousands and thousands of dynamic systems that are changing to make sure that we are able to deliver the beam that we need to deliver.
Well, and you say thousands and thousands of systems. It looks like there are thousands of things going on right now. How does one monitor all of this kind of stuff, right? I mean, from someone that is, on the outside looking in, I'm looking at this and I'm thinking to myself, where do I start?
It's a nightmare, yeah.
Yeah.
So we have a sort of a heads up display right here where it's showing all the things that could go wrong in a common place. So we see everything here is green. That means that no system is reporting that it's out of sync to where we want it to be. And sometimes we will have a failure. The source machine could break in such a way that this some device turns off, and therefore nothing else works. And so we'll have one of these squares turn red, and then we'll know, oh, this sort of device needs to be reset, and then we'll be back up and running.
So let me reword what I believe you just said. So here, right, these two are yellow. And what that basically means, like, hey, it's not bad, but just let's watch it. Let's see what kind of goes on. And that will have me as the user say, okay, I know what plot to look at. I look at the plot that correlates to that.
I will say that the yellow is actually just a coincidence. It's just something that's not quite receiving the signal it expects to receive. So it's actually working perfectly fine. It's just that's what's showing up on.
But if it did turn red, that would be the way to track down where I got to look.
So the users wouldn't necessarily be the people that are responding to the issue of the accelerator. That's on us, for us to make sure that these systems are working. And so we'll contact people that are responsible for those devices, or we'll make the changes ourselves to make sure that everything's back in its expected condition.
Now, this seems like it's like the main display. This is kind of the mothership of monitoring things. But you have a bunch of other stuff going on here. What is this other stuff?
Right, yeah. So this plot is monitoring the source machine and some various outputs that they use. These Burgauss injection, extraction, that's just showing the intensity of the beam over time. So if we see some big dips here, then we can know that maybe it's unintentionally fallen out of sync with where it's supposed to be. So it's just a way for us to monitor everything is working as it's intended to. We also have displays here to show the beam fluence over time. So right now it looks like there is no beam. This is below zero. So they might have paused it momentarily, or it's just a very low intensity. You see we're barely up to 50 ions per centimeter squared per spill, which...
And you can see it tracking in real time, right?
Right, so it's updating as we speak. So every cycle of the synchrotron, right now it's like a 3.2 second cycle. Every cycle involves shooting the laser on that chunk of metal and accelerating it and extracting it. Every 3 seconds, we're starting from scratch.
And then right there.
So they've turned the beam on, and they're probably trying to hit around 100 ions per centimeter squared per spill. It must be a very sensitive test that they're looking at. And then there's nothing that's changed on here because the source is constantly running, even if they turn the beam off.
I see a lot of connected pieces here. Are these boards actually powered on, or are
Yeah.
they? Okay, so
Yeah.
this is not just a board that is unpowered. It is actually functioning,
Exactly.
and that's being exposed to radiation.
And that's how you can actually determine that something has failed. You'll be looking at maybe waveforms coming out of the device, or you'll be writing data and reading data. And if there's a disruption, that's how you know that something is broken. So if you had the device turned off, you couldn't really tell when this event took place. And so that's necessary for diagnostics that these are running. And it's also important to have them operating because the computers require stable voltages, right? So if you're running a processor, it needs to be at a certain level of power that it's receiving. And if you hit something on the board which changes that power delivery or the amount of voltage it's drawing, that'll create an event. And then they can tell that something went wrong.
Thanks for taking us once again behind the scenes of what is actually going on with this radiation testing. So really appreciate it.
Absolutely.